All right, so with conic sections, you've seen this before. All the things you can do by taking two cones and putting them together, inverting one on top of the other, that you can show almost everything in geometry. You've seen that. So if you take a plane, the intersection at where the two come together is a point. If you take the plane along the edge, you have a line. If you slice the two cones down the middle, you have two intersecting lines, or a line pair, they call it. If you slice it parallel to the base, you get a circle. If you tilt it, now this is, I had never seen this before, but if you look at the angle between the cone and, or the edge of the cone and the altitude, we call that beta, and you look at the angle between the altitude and the plane, if alpha is bigger than beta, you're going to get an ellipse. If it's equal to beta, it's a parabola. Yeah. Okay, so this is the angle beta, that's the angle altitude to the cone, right? And you have this plane that's intersecting. Now, if you can intersect parallel to the base, then it's just going to be 90 degrees with the altitude. It'll be a circle. But if that angle with the altitude is greater than beta, it's going to be an ellipse. But if you tilt it more so it's parallel, this becomes, it doesn't cut the cone in two places, it just cuts it kind of off here. It makes a parabola. This parabola is a very unique case. Then, if it's less than, the angle alpha is less than beta, now you're going to cut the top and the bottom one, and you get what we call a hyperbola. So those are the conic sections, they call it. I don't know what they're talking about, degenerate conics. I don't really want to. Sounds scary to me. Yes?
So is the only difference between a parabola and a hyperbola that one of them has an upper bit?
I love that question. I'm going to answer that right now. Okay? That's one way of looking at it, is slicing two cones. Okay? And Oliver's right. You notice that the hyperbola does have two parts to it, where the parabola only has one. That is one element of the distinction between parabolas and hyperbolas. But the shape itself is different. Okay? And one way to do that is to look at what we call the focal point and the directrix. Now, a directrix is a line. Remember when we used that distance formula, we needed a point and a line? Okay? We're not taking the shortest distance. We're going to take a point P somewhere between the line and the focal point. And if you draw a perpendicular to that point from the directrix and then connect it to the focal point, you're going to get two line segments. Those line segments will have different lengths to them. And if we call this N and this the focal point F, you take the ratio of PF over PN, you're going to get something we call the eccentricity. And that is what distinguishes hyperbolas from parabolas. If your parabola, if E is equal to 1, if this length equals that length, focal to the point equals point to the shortest distance to the directrix, that's a parabola. But if the ratio is less than 1, in other words, PF is smaller than PN, then you're going to have an ellipse. If PF is greater than, it's, think of it this way, is you've got this parabola if these distances are equal. I didn't draw that right, but it's kind of what you do. And that parabola, if you widen it out more, then this is going to, PF is going to be greater than this. Widening it out makes it a hyperbola. Shortening it up makes it an ellipse. But that's the distinction that we're going to make. Let's talk about that. I don't know a lot about the focal point, but I do know a little bit of physics. And if you take a parabola and make it out of glass, and you take a bunch of parallel lines. Have you seen this before in physics? I hope. I don't know why that's doing it twice. A true parabola is going to, each of these are going to reflect to the center. And if you have, and I know I didn't draw these perfect, it's not going to look good, but this is the ideal, is that each of these angles are equal to each other. If I drew a perfect parabola, each of these angles are equal. Angle of incidence equals, well, yeah, angle coming in equals the angle going out. Those reflections are going to reflect that to the, and then you have a reflecting telescope. Much more powerful than a refracting telescope because you can gather more light with it. If you take a telescope this big and look through it, that's all the light you can gather. But if you have a reflecting telescope this big, you can gather all that light and things are going to be much more interesting. Like what they would do is they would have a little mirror here, and then at least on this side, the light's going to be reflected to an eyepiece, and then you could see, work late at night, and you could see the image. But anyway, does that help what the focal point is, or not at all?
Yeah, so then the point P on that diagram.
Is a point on the image. So we're going to do one. I just made this morning. I hope it's on your download. Do you have it? Oh, good, good. We're going to draw one of these. You might have to help me out here. I think I made the lines a little too dark. But this is the directrix here. And this is the axis, x-axis. We're going to call this 4, 0 the focal point. So this is going to be my F. And you're going to make some points here. So from F to the directrix, PF over PN is going to be 1/2. So if we go 1, 2, 3, 4, 5, 6, 7, 8, that isn't real helpful. If we go out 1, 2, 3, and let's see, 1, 2, 3, 4, 5, 6. And let's see, what we want to do is I want to, yes, here we go. So let's go out 2 here. 1, 2, and go 6. 1, 2, 3, 4, 5.
Yeah, so from the y-axis.
Okay, I called this 1, 2, 3, and 4, 5, 6, 7. And this is the directrix here. We're calling it 0, but they're saying it was just the y-axis. We're going to call this the directrix here. And maybe this isn't going to work, but we're going to try it. So let's go over 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay? And here's 8. And we want to go up 4. 1, 2, 3, 4, right? 1, 2, 3, 4. Okay, so if I go over 8, 1, 2, 3, 4, 5, 6, 7, 8, up 1, 2, 3, 4. This is a point on that figure. And by the way, if you go down 1, 2, 3, 4, it's going to be the same. Okay, let's go out, up, go 6. 1, 2, 3, 4, 5, 6, and we're going up, out 3. 1, 2, 3. I don't think, oh yeah. 1, 2, 3, 4, 5, 6. Out 3 comes down to here. That's going to be the next one. Remember, it's got to be 1 to 2. So let's see, this is going to be down here. And if we continue, you can kind of see this shape coming. Then if we keep going, go 7. 1, 2, or let's see, what would be easy to do here? We did 4, 5, and 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5. It's going to be about right there. And we keep continuing out. Let's go 12, 2, 4, 6, 8, 10, 12, and then we're going to need to go up 6, or out 6. 1, 2, 3, 4, 5, 6, which is going to be about here. Oop, I don't think so. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Yeah, it should. Why do those look so different? 1, 2, 3, 4. Did I get this one too low? This one looks too low. Anyway, if you keep doing that, you're going to get the ellipse shape. That's where the eccentricity PF over PN is equal to 1/2. And when we're drawing these, this is a way to specify those. One more time, if P of F over P of N equals 1, that was your parabola. When it's equal to E and E is between 0 and 1, it's less, we get an ellipse like you saw. If it's greater than 1, then you're going to have a hyperbola. So for the next couple minutes, consider a parabola with vertex 1, 1 and focus 3, 3. Sketch the parabola on the set of axes. Find the equation of the directrix and find the equation of the parabola. Okay, so let's do a little drawing here. And we have 1, 1 and 3, 3. This one's kind of neat. And this is my vertex. And this is going to be my focus. Going back, it said that if you took PF over PN, if you took a point on that, and if you look at what we had in that problem, they had a focal point, and then they had the vertex, and then they'll have the directrix, right? So if you knew this point, could you find the directrix? At least this point of the directrix. Could you find that? Could you do that? If we knew this one, could we find this directrix? Yeah, and how would we do that? How do we find this point? You know it's somewhere along this line. you know this is down 2 over 2, so if we go down 2 over 2, what will this point be? Negative 1, 1. Yep. And negative 1, negative 1, right? No, that's okay.
So why is the directrix that in that line? Why is it not farther closer to the vertex?
Because for a parabola, this distance here, this is F, this is P, this point here is going to be my N. This distance has to be equal.
So it's 1.
The eccentricity is 1. So we know that this distance here is going to be the same as this one. So down 2 over 2, down 2 over 2 will get you this point. What's this slope going to be? What's this slope? 1. So what will this slope be? Negative 1. So the equation of the directrix is just going to be x minus negative 1 times negative 1 equals y minus 1, negative 1. So I think this is just going to be negative x minus 1 equals y plus 1. So you're going to get negative x minus 2 is equal to y. All right, now it says find. So we've got this sketched. Now we need to find the equation of the parabola.